Hello everybody, welcome to Joy of Calculus episode 2. Today we've got area between two curves. Now this is actually a pretty simple concept. It's not a whole lot different from normal integrals. Consider two curves, g of x and f of x. First curve, we've got g of x beneath f of x. Look at that region right there, a to b. Second curve, f of x. It's a little bit higher. F of x is above g of x in this little example. So just consider this. We've got these two regions. One is for f of x, and f of x is above g of x over a to b. Take a minute and look at that. F of x is above g of x over that interval. And if you consider the area between them, the one that's caught between f and g, we could actually find what that area is by taking the integral of f of x and subtracting the integral of g of x. And what that ends up being equal to is f of x minus g of x. And that's actually the formula that we're going to use. You can kind of sum it up as basically the integral of the top curve minus the bottom curve. From a to b, whatever integral's over. There's something I need you guys to know though about this. It can get kind of tricky in a few spots. This lesson is a little bit, well, simple in parts and then extremely challenging in other parts. I need you to know that sometimes curves can switch in terms of which one is greater than the other one. So consider this graph right here, of which I'm just going to draw a quick sketch. By the way, as an aside, these are really good functions that I drew. I'm pretty proud of how good these look. Anyway, so consider that as f of x right there. And then consider this curve right here as g of x. Now, as you can see, consider that area bounded between them. You can see it as those two kind of oval-looking things, but not quite ovals. Now, that point right there is where these two curves kind of switch. In the first region, you can see that f of x is above g of x. In the second region, g of x is above f of x. And that actually necessitates two separate integrals. One integral is for the area on the left, one integral for the area on the right. So just remember that as you go through the homework. Good job. Next thing. Our first example in this is to find the area of the region between f of x equals 2 minus x squared and g of x equals x. So what we're going to do, I'm just going to draw a quick sketch of these. If you encounter a problem that's set up like this but they don't give you a graph, I would really encourage you to well, get a graph yourself, either by using your calculator or drawing one by hand. But what's important about this problem is that it's bounded between these two curves, so it's that area right there that I'm filling in. But they don't actually give you the a to b. You don't know where f of x and g of x actually meet, which is what defines this problem. We'll have to go in and find what those two x coordinates are that let us set up our integral. But we can set up part of it. Because f of x is the one on top and g of x is the one on bottom in this case, I set up that integral in there, 2 minus x squared, and then minus x. Now at this point I'm kind of locating to myself, where are the x coordinates? I'm not looking at the graph because I don't trust my graphing skills. They might not be too exact. So let's turn to the algebra and let's see if we can get the exact x coordinates. We're going to find where these functions meet by, well, setting them equal to each other. So we're going to write 2 minus x squared equals x. And then what we're going to do is move the 2 and the negative x squared over the other side. And we're going to obtain from that 0 equals x squared plus x minus 2. Just moving things to one side, getting it equal to 0. Pretty standard algebra technique. What we're going to do next is factor. And this factors into a pretty nice x plus 2 and x minus 1, which gives us two zeros for this region right here. We have one solution is x equals negative 2, and one solution is x equals positive 1. And then I'm going to go back up into my sketched graph there, and I'm going to label those points. So negative 2 right there, and then that's 1. And that will pretty much let me start doing the integral now. I know the bounds. It's negative 2 to 1. So first thing we're going to do is rewrite this slightly to make it nicer to look at. Negative x squared minus x plus 2. Now let's do the fundamental theorem. So negative 1/3 x cubed minus 1 half x squared plus 2x from negative 2 to 1. And that gives us, well, a string of, not too complicated, but they're still fractions. It's kind of annoying. We end up with negative 1/3, negative 1 half, plus 2. That's for plugging in the 1. Then minus, plug in the negative 2. It's negative 1/3 times negative 8, minus 1 half times positive 4, plus 2 times negative 2, which is negative 4. And this actually all ends up being 9 halves, which is 4.5. All right. Next thing that we're going to end up doing is probably the hardest part about this, this particular section of the chapter. Okay? And it involves finding the area of a region two separate ways. One is with a dy integral, and one is with a dx integral. So be on the lookout for that. Notice these two functions right here. Got 3 minus y squared and y plus 1. So these are functions in terms of y. That first one is a parabola. Now, usually they'll give you graphs for these, so you just have to determine which one. And I know that that function is x equals 3 minus y squared, because that's a parabola looking one, sideways parabola. And that one right there is x equals y plus 1. Now the formula for finding the area between two curves that are sideways is a little bit different than the top minus bottom one. So just watch for that in a second. Right here I'm just letting you know that there are two ways to do this, and we're going to go through both of them. And go through the y's a little bit more in depth. We'll do the y's on the left hand side there. Then the x, I'll just tell you what the trick is for that you have to consider. What I'm doing right now is just re-solving those two functions for y instead of x. So instead of x equals y plus 1, I'm rewriting that line there as y equals x minus 1. So just subtracting the 1 over. Then the parabola, I'm solving for y for two separate equations. So I add the y squared over, I subtract the 3, then I take the square root. The top half of the parabola is positive square root of 3 minus x. The bottom half of the parabola, if I solve it there, it's going to end up being y equals negative square root of 3 minus x. Okay. Now that I've set up both of those, let's start by finding the y integrals here. And this is kind of confusing, but just know that we're going to start by doing the right integral minus the left integral. So right function minus left. And the trick with this, though, is that because it's a y integral, we have to respect the y bounds of the region. You can see that my y bounds here are going to go from that bottom part of the point, negative 2, all the way up to 1. So I'll sketch in some lines for where this region is going from and to, and hopefully you should see from that that it's y as negative 2 up to y equals 1. We've got a line so from negative 2 and steadily accumulating these little rectangles from negative 2 all the way up to y equals 1. Now, the kicker with this y integral is that, like I mentioned before, instead of top minus bottom, there's no top minus bottom here. It's got to be the right minus the left. When you have horizontal functions like this, it's the right function that's larger than the left. So I plug in 3 minus y squared minus, and the quantity y plus 1, from negative 2 to 1, as I previously discussed. And reiterating again, right minus left. We perform the fundamental theorem. Well, rewrite the integral first. Want to make this easier to antiderive. So I rearrange some things, combine negatives, distribute negatives, all that good stuff. We get negative y squared minus y plus 2 dy. And now you just integrate it like a normal x integral. It just has y's instead. The name of the variable doesn't matter. You still perform the same techniques. Made a little error there. And so negative 1/3 y cubed is our first part of the antiderivative. Then minus 1/2 y squared. plus 2y from negative 2 to 1. And you end up doing some math there, or you can use a calculator, finint it even if you want, and you actually end up that this area is 9/2, or 4.5 again. Happy day. The next piece here is the x integral, and this is where it gets, I wouldn't say more difficult, it's just there's more steps to it, I guess. First thing you have to do is consider that this actually splits into two separate sections. Hopefully you can see that dotted line right there, splitting it up into two separate sections. The first section is x equals -1 to x equals 2. I'm drawing it in right there. I have to do that because the x minus 1 function stops being the top function at that point. So the first thing I'm calculating is that area, -1 to 2 for an x integral of x minus 1 minus the bottom function, which is negative square root of 3 minus x. I set up my next integral, which is going to go from 2 all the way over to 3, and here's where it gets tricky. I have to do the top half of that horizontal parabola by doing square root of 3 minus x, minus the bottom half, which is minus negative square root of 3 minus x. And I'm going to calculate both of those integrals separately. I'm going to write out some of the work that you get by doing the fundamental theorem. It's a little tricky. Again, I'd recommend for a lot of these problems you actually turn to finint for them on your calculator. That's Math 9 in case you forgot. You'll see me write some numbers here. Those numbers come from plugging numbers into the antiderivative using the fundamental theorem, techniques that you guys have seen before. But for these types of integrals, sometimes they can get pretty complicated with a lot of calculations. So again, reiterate, please feel free to use finint. And what you should get is 4.5 by integrating in this opposite direction in terms of x with the dx. Again, remember, feel free to use your calculator. Finint is perfectly fine. Last thing, if you guys have any questions about this, feel free to take a look at page 452 in your book, specifically at example number 5. That's the example that I went over right here, and it has a few more steps in there, and it's a little bit, well, it's a static image, so it should let you take a look and ponder what the steps are at each point in the problem. Okay, let me know if you have any questions. Feel free to send me an email or anything like that. Have a good day.